Now, here is a periodic table. It's only the first three rows of the periodic table. You will see that there's actually a little break here like you would normally see on a periodic table. But it kind of shows the Bohr models of the elements in these first three rows. And there are a couple of patterns. First off, if you look at families here, so this family right here, the alkali metals, they all have the same number of valence electrons. Okay, they all have the same number of valence electrons. So hydrogen has one, lithium has one, sodium has one. You go to the next family over, the alkaline earth metals, and they all have two valence electrons. This is actually kind of the characteristic that makes them a family. So beryllium has two and magnesium has two, and this continues all the way down. They have the same number of valence electrons in each family. So those valence electrons are important for what those families are. Now, if you look at the rows, okay, the row that it's in will actually tell you how many orbits it has, how many shells, and that's what this slide is actually saying. So this first row here only has hydrogen and helium. Both of those only have one orbit, one shell. Okay. The second row of the periodic table, or second period of the periodic table, you will notice that you can only fit 8 electrons in the second orbit, and you only have 8 electrons in the second row, or period, of the periodic table. That's because as it moves down, you add an electron each time, you get another electron that's being added to that second orbit here. Okay? When you get to the third row, or the third period of the periodic table, all of these have 3 orbits, and it's filling in that third orbit in this third row. Now, this will have more than 8 electrons because you start filling in that D, but you don't fill in that D until you have some electrons in the outermost shell for that fourth orbit. So this is essentially representing just the outermost shell, the valence electrons here. So 8 valence electrons is kind of the maximum you can possibly have with any element here. So it's kind of representing that. Now, if you go to the whole periodic table, we talked about the S and the P's and the D's and the F's. You can actually start to see the pattern here in the periodic table of the electrons. So everything over here, everything over here has as basically on this little section of the periodic table is ending with that S shape. So everything over here is essentially P shapes. Everything over here has some D shapes, so they're filling them in as you go along. And everything over here would have those F suborbits as you fill it in. So there actually is a pattern here, and we'll go over that in a little more detail in the next set of notes. Now, atomic radius. Atomic radius is essentially the size of the atom, not its mass, but its like volume, how big it is. Now, in order to measure this, we use an electron microscope. And when you look at atoms in an electron microscope, they're kind of blurry, and it's hard to actually tell where an atom ends. So, and there's also usually a ton of them there. So usually what we see is kind of these lumps on a flat surface, and we can't really see where one ends and the next begins. So what we do is we find the centers of those atoms, and we measure the distance from center to center. Okay? So if we have the distance from center to center of 2 atoms that are the same element, then those atoms, if we just divide it in half, that would essentially be where the edge of the atom is, the radius, the center to the edge of that atom. We would essentially have it for both those atoms, but that's how we measure it. Now, when we measured the atomic radius of these elements, we noticed kind of an interesting pattern. Okay, so here is the pattern of a whole bunch of elements arranged in the periodic table. Now, you will notice that as you go down from row to row, they get bigger. That's not really unexpected. They have more orbits. But what's interesting is as you go across a row, then they actually get smaller, which is weird. It's very weird. So let me just focus on that going across a row thing here. Key feature here is that everything in the same row has the same number of orbits. Okay, so this is the second row of the periodic table. And everything in the second row of the periodic table has 2 orbits. So as you're adding electrons here, lithium to beryllium to boron to carbon to nitrogen, you're adding an electron into that second orbit, but you're not adding any orbits. Okay? Essentially, we found that atoms only get bigger if you add an orbit to it. So they're only ever going to get bigger by going and adding another orbit to this atom. That's it. That's the only time they ever get bigger. So why do they get smaller, though? Well, this actually has to do with what you're adding. You're not just adding electrons, you're also adding protons and neutrons in the nucleus every time you go from element to element. And as you go from element to element, this has 3 protons in the nucleus. So it's 3 protons attracting these 3 electrons here. But if we again go to a couple more down, this one here is carbon, has 6 protons, literally double the amount of protons. So it is a stronger attraction in that center. And this first orbit here still only has 2 electrons. So these 2 electrons are attracted to the nucleus, but there's more protons in the nucleus here than here. So these 2 electrons are actually going to be even closer. This orbit will actually be even closer to the nucleus than it was for here. The second orbit, it still has 2 orbits, the second orbit will also then be closer to this nucleus. So as you get more and more protons in the center, it actually pulls the orbits inward. It becomes closer and closer. It gets denser. So this pattern here is that the size, or the atomic radius, actually decreases across a period. You're going to have the same number of orbits here, but as you get more and more protons, it pulls all of those orbits closer and closer. So more protons in the nucleus just increases that pull on the electrons, and it pulls them in tighter. So all of the orbits, not just the first one, but it's all of the orbits, the one on the outside too, get pulled in even closer, making the whole atom smaller. Not smaller in mass, smaller in volume, in its size, its radius. Okay? Then as you go down a column in the same family, you add an orbit every single time. So every time you go to the next row, you actually get another orbit, which does in fact make it bigger, which kind of makes sense. It's only the other one that didn't really, you have to kind of explain here. So add an orbit, it gets bigger. So the biggest atoms are going to be in the last row, but they're not going to be all the way to the right, they're going to be all the way to the left. Okay? So it increases as you go down a row. This is because you have more orbits. All right? Now there is something here called electron shielding. As you add orbits, as you add these energy levels, it actually decreases the outer electron's attraction to the nucleus. Okay? So this outer electron here, this one right here, it actually is being attracted to the nucleus. And although there are more protons in here attracting it, this one has 11 protons, it has 2 orbits in its way. 2 orbits of electrons kind of shielding it from being able to be attracted to that proton. So it's kind of like if I had a very, very powerful magnet in the center or something, but then I put stuff to block that magnet from being seen. Even though it's attracted to it, there's going to be stuff that kind of forces it and keeps it from getting too close. So this is called electron shielding. The more orbits you have, the more electron shielding you're going to get. Okay? So this one actually has greater electron shielding than this one. This electron only has basically 1 orbit in its way to the protons, whereas this electron has 2 orbits filled with lots of electrons, 10 electrons to be exact, in its way. Okay, so this one is actually less attracted to its nucleus than this one here. So this orbit, because it's a little less attraction than this one, it is actually further away. It's a bigger atom here because of that electron shielding. So let's try a few. Which one is bigger? I'm going to name 2. I want you to tell me which one is bigger, larger, has a larger atomic radius. So the 2 I want to name, magnesium and sulfur. Got an answer? So, magnesium and sulfur, they are in the same row, which means they both have 3 orbits. Okay, so magnesium's right here, sulfur is right here. Because they're in the same row, sulfur has more protons. Same number of orbits, but more protons means it's going to be smaller. So the smaller one is going to be sulfur, and the larger one is going to be magnesium. So which is larger? Magnesium. Let's try another one. What about fluorine and chlorine? Which is larger? Got an answer? So fluorine and chlorine are in the exact same family. Fluorine's right here, chlorine's right here. So fluorine has 2 orbits, chlorine has 3 orbits. The 3 orbits is going to be larger than the 2 orbits because it's got 3 orbits. It's got more electron shielding, so that other orbit is going to be further out, making the whole atom larger in terms of radius. Now let's talk about ion. Okay, now an ion is any atom that gains or loses an electron. So this atom right here, which had 11 electrons, if it loses one of them, it doesn't lose any protons, then it would be positively charged because now it has an unequal amount of protons and electrons. Okay, so it is possible to take electrons away or even add electrons in. And when we do this, it's always going to be the valence electrons that are affected, right? It's either going to be the valence electrons that leave, or you're going to add more, giving you more valence electrons. So it's all about the valence electrons here. If you gain electrons, you actually become negatively charged because electrons are negative. If you lose electrons, you become positively charged because now you have more protons than electrons if you lose some of those electrons. All right? So what happens to the size of an ion when the atom loses or gains these electrons? Well, it's actually 2 different things. It either gets bigger or smaller. Okay? Positive ions, the ones that lose electrons. So, for example, lithium here, which normally has 3, 1 valence electron. If it loses that valence electron, now it only has 2, it becomes positively charged. Okay? And now, because it lost a whole electron, it lost its outer orbit, it now has only 1 orbit. Okay? It was 2 orbits, but when it loses that electron in that second orbit, it doesn't have an orbit, there's nothing there. So now it only has 1 orbit. That would make it smaller. All right? Anytime you lose electrons, the positively charged ion that you now have is smaller than it was before because there's less electrons, there's going to be less orbits, so it is a smaller thing. Now the exact opposite happens with negative ions. These are the ones that gain electrons. So here's my regular atom, fluorine, and if I add an electron to that, there is now the same number of orbits here, 2, but you have an extra electron in that second orbit. And since electrons don't like each other, but I didn't add a proton to the center, there's no more protons there, there are now more electrons in that second orbit attracted to the same number of protons. They're basically competing for those protons. And so because they're competing, they will actually kind of expand the orbit, making that orbit much, much bigger because there's more of them pushing each other away, trying to make room for themselves without a proton, an extra proton, pulling them in closer. So the whole orbit, that whole second orbit, will then expand, making the atom bigger. So a negatively charged ion, one that gains electrons, is actually going to be larger than it was before, larger than the neutral atom. So if it's positively charged, it's going to be smaller. If it's negatively charged, gained electrons, it's going to be bigger.